Okay, we just started talking about how two coils can interact with one another, where we have a primary coil inducing a voltage in a secondary coil. But there's another phenomena which is very much related. We also measure this type of induction in terms of Henrys. But anytime that we produce a magnetic field, we are creating energy in this field, or we're storing energy in this field. It takes time for this energy to build up. This produces what we call a back EMF. And it means that if we try to get the current moving through an electromagnet, some coil of wire, which is going to generate a magnetic field, the current isn't going to go through the circuit instantaneously. That would imply that the magnetic field suddenly appears, and that violates the conservation of energy. So anytime we generate a magnetic field, it's going to take time for the energy to go from electrical energy in the form of a potential and moving current into magnetic energy, which produces our magnetic field. Okay, so let's take a look at this and see how this works. Self-induction occurs anytime we get a changing flux through some coil of wire. Again, it can be, actually, it doesn't even have to be a coil of wire. A single wire will produce a magnetic field. But anytime we produce a changing flux of magnetic field, we will get this idea of self-inductance. As the current increases, the magnetic flux through the loop to the current also increases. The increasing flux induces an EMF that opposes the changing magnetic flux. Okay, this is actually going back to Lenz's law, that when we create a magnetic field, any loop of wire is going to oppose that change in magnetic field. And again, it's due to the fact that the magnetic field can't just spontaneously appear out of nothing. And as the current increases, the rate at which the magnetic field increases will decrease too. And again, the decreasing EMF gradually allows the current to increase. So self-inductance looks like this. Here's our equation for self-inductance. The EMF induced in whatever's going to produce a magnetic field, usually a coil of wire, okay? The EMF that is generated, that is going to oppose the current flowing through, is equal to this constant right here, which is basically inductance, okay, or self-inductance if you want to completely use the full term. Usually we just refer to it as inductance. Is the inductance of whatever circuit element we're using times the change in current divided by time. All right, really the rate of current change with respect to time. So L is the inductance, and the negative sign indicates that we have Lenz's law going on here, that the magnetic field that is trying to be created within this loop of current, okay, the EMF is going to point in the opposite direction and oppose the buildup of that current. And again, just as we saw before with self-inductance, it's measured in the Henry, and Henrys are volts per amp per second. All right. Now you can determine an expression for L, where L is the number of loops that we have. Obviously, the more loops of wire that we have, the more intense the magnetic field is going to be, times the magnetic flux through the coil per amp of current. Okay, so you're going to generate magnetic flux inside here. Obviously, the more turns that you have, the more intense the magnetic field is going to be. But also, it's going to depend on how much magnetic flux you get for a particular amount of current. Okay, So again, one way of understanding self-inductance is the voltage produced is related to the change in the current. And again, we can think about this all in terms of energy. We've got some battery right here and maybe a switch where it is going to put energy into the circuit. Now, initially, this loop of wire has no magnetic field going through it. And as the current starts getting going through the circuit, okay, that magnetic field will start building, okay, will start building inside here, getting stronger and stronger as more and more current can flow through. But again, the current can't be instantaneous, because if the current suddenly just starts going, that indicates that the magnetic field suddenly goes from 0 to some point up there. So in fact, later on when we look at induction circuits, what we're going to see is that in graphing our current as a function of time, what we're going to see is that the current is going to do something like this. It's going to, oops, I'm still drawing with lines. I'm going to take that away. But again, we're going to graph current as a function of time. But what we're going to see is it's going to take time for that current to build. And then finally, when that magnetic field reaches its equilibrium point, that current is going to reach its maximum value as prescribed by Ohm's law, where I equals V over R. R would be the resistance of the wires in the circuit. V would be the voltage from the source. So again, what we see here is it does take time for this magnetic field to build up. So what actually happens, again, is we have a positive and negative voltage from some outside source of EMF, and that is going to produce a positive and negative EMF by Lenz's law in the loop of wire, which is going to initially oppose the movement of current. All right. Now, the most common type of circuit element, which is designed to be an inductor, we'll see why inductors are important for different things. Obviously, inductors are important for motors, are important for generators, are important for relay switches. But you can actually have inductors placed in a circuit for a variety of different reasons. But the most common type of inductor that we come across is just simply a solenoid. Now, A is a cross-sectional area, while L is the length of the solenoid. And earlier on, we saw this equation right here for the magnetic field produced by a solenoid. And of course, if we multiply that by the area, we get the magnetic flux. Now, again, let's go to our definition for self-inductance. The self-inductance, or the inductance of a circuit, is equal to n, the number of loops, times phi, which is the magnetic flux that's produced inside the solenoid, divided by I, which is the current. Okay, so when I plug this equation into here, I've got an I in the numerator, I've got an I in the denominator. That I will cancel out, and the inductance, the mutual inductance, just becomes this equation right here. So if I want to know how many henries a solenoid will produce, this is a solenoid without a ferromagnetic core, it's going to be mu0 times n squared, n being the number of loops that we have, times the cross-sectional area divided by the overall length. Okay, so that is the mutual inductance for a solenoid. And the solenoid doesn't have to be a cylinder. In this case, we have a rectangular cross-section, or roughly rectangular cross-section. But if we add a ferromagnetic core we can actually increase the inductance of the circuit. And what that effectively does is, if mu is greater than mu zero, which it is for ferromagnetic materials, we can get a larger magnetic field inside the core, and therefore a greater amount of self-inductance. One of the problems we have with mu, which is a permeability, this is the permeability of free space, this is the magnetic permeability, is that it's actually a function of the magnetic field. So, mu will vary as we send more and more current through there. So, this expression is a little more difficult to know exactly what it's going to be, or I should say, it's really a function of how much current is going through there. So it's a more difficult equation to use. Here's an interesting toroidal. This is a toroidal inductor with a square cross section, and I'm not going to go how you get how you derive this, but it actually comes from integrating. Obviously, it's when you're integrating a reciprocal, you get the natural log, but again, you can get different types of inductors of different shapes. Here's a square toroidal inductor. And of course, as we said before, motors and generators also have coils of wire, so they're going to have a large self-inductance. Now, this is important. When you first start up a motor, basically, there is going to be a large back EMF from starting this up, and it actually takes more energy to get the motor going than it takes to keep the motor rotating. And this actually creates a problem for some of these motors, because if the motor doesn't get enough energy to start rotating, okay, the self-inductance, because the magnetic field isn't changing, self-inductance may be very, very low, sending more current through the motor than it's designed to take. And if the motor seizes up, essentially the coils of wire, instead of generating a magnetic field, will simply become heaters. The motor will overheat and it can actually start a fire. So it's very, very important anytime that you use an electric motor that you have a motor that can spin freely. The bearings are in good shape. There's nothing caught in the motor, because if a motor seizes up, this can basically turn the motor, which converts electrical energy into work, into a heater, which converts electrical energy into heat. So again, thinking about this, the phrase back EMF, it's used to indicate the voltage which is generated when you first turn on a motor, or the voltage which is going to be produced by a motor if you're using an alternating electric field. So let's take a look at this. Again, when the motor is first turned on, there's no back EMF initially, basically because the motor's not spinning, so there's not a changing magnetic field. So in this case, again, if it doesn't start spinning, we have a 120 volt source, we have 10 ohms of resistance. If we do our calculations here and see how much current flows through the circuit, okay, current is equal to voltage divided by resistance, 120 volts divided by 10 ohms. Okay, when this thing first starts out, it's going to take 12 amps of current. Okay, and where's that energy going? Well, that energy is simply being turned into heat. All the power is being converted into thermal energy. As a motor starts going, then the back EMF due to the induction might jump up to 70 volts, which means that now, instead of the voltage pushing current through the wire, we have 120 volts minus or 70 volts. So we have a total of 50 volts instead. And we drop from 12 amps to more manageable 5 amps. And most of that resistive energy, again, we've gone from 12 to 5. Our power, which is being turned into heat, has dropped by a factor of also 5 here. So once this motor gets going, it's not losing as much energy due to heat. So again, this shows you a few things. First of all, when the motor first starts up and there's no back EMF, we need a lot of large current to just get this thing going. Okay? So what the circuit may be rated for, which is powering this motor, might be more than the motor actually operates at when it's actually going. And again, if it's seized and that back EMF never gets going, more current will go through the wires than it's designed to take, and the motor will get very, very hot and it can start a fire. And again, as we said, as the coil begins to rotate, the induced back EMF opposes the applied voltage, the current is reduced, and the power requirements for, so of course, the power requirements for starting the motor and for running under heavy loads are different, okay? The power to start is much greater than the power to keep it going.